Welcome back. This is our sixth video in our quantum measurement problem video series. I'm Dr. Michael Steiner, and I work with Dr. Ronald Rendell on the investigation of the measurement problem. Our measurement problem video series is designed to complement our book, The Quantum Measurement Problem. In this presentation, we will examine the importance of the scientific approach in general terms, particularly the strengths and weaknesses of inductive versus deductive reasoning will be explored as they relate to the measurement problem. In the general sense, there are two scientific approaches that we will consider, that of inductive and deductive reasoning. Inductive reasoning is a method of generalizing specific results towards more general conclusions. For example, in the sequence 1, 3, 5, 7, the next number might be concluded to be 9 via inductive reasoning. Many people use inductive reasoning on a daily basis. They are extrapolating further based on their current knowledge. Deductive reasoning, on the other hand, is a method of using general results to reach a specific conclusion. This requires a process of eliminating incorrect results until a single choice remains. It is not often used on a daily basis. Given a set of valid assumptions, deductive reasoning always reaches correct conclusions. On the other hand, inductive reasoning may be wrong. Suppose one is given the first four terms of a sequence S and told to determine S of 5 via induction. Well, if S sub n are simply odd numbers, then concluding S of 5 equals 9 via induction would be correct. But suppose S of n are the roots of the polynomial S of x equals the product of x minus 1, x minus 3, x minus 5, x minus 7, and x minus s of 5. And, furthermore, let us suppose s of 5 is different than 9. Then reasoning that s of 5 equals 9 via induction would be incorrect in this instance. When developing new fundamental scientific theory, one must be careful not to fall into the pitfalls due to inductive reasoning. Inductive reasoning is intuitively appealing. Conclusions are based on generalizing current theory, and therefore typically are consistent with the current grain of thought. Deductive reasoning is not necessarily intuitive. It is possible to draw conclusions that are against the current grain of thought. In fact, with every claim of a major new discovery, there are generally arguments put forward against the claim. Arguments put forward against the results of the new discovery are often based on inductive reasoning. Fundamental science for many years was a deductive process and engineering an inductive process, not guaranteed to produce an optimal, ideal, or absolutely correct engineered design. In these times, science has largely merged with engineering, in the sense that problems are mostly being solved in both areas inductively. There are many people with outstanding inductive reasoning skills. However, this does not guarantee that the deductive reasoning skills will be outstanding. Many people have tried to solve the measurement problem with inductive reasoning. Inductive reasoning may not be a good methodology to use in fundamental physics to discover new physical laws and/or principles. Here are potential examples that illustrate why. The conclusion that because a feather falls slower than a lead weight on the earth, that the acceleration solely due to gravity must be proportional to mass. Concluding, before Einstein's relativity theory, that because we do not typically observe in daily life matter converting to energy, that it is impossible for it to occur. Concluding that alchemy, or the conversion between different periodic elements, is physically impossible before the understanding of nuclear processes. Concluding before Einstein's discovery of the photoelectric effect that threshold effects do not exist, and lowering the frequency but increasing the intensity will be able to cause photoionization of matter. Concluding before the discovery of atoms that because we cannot see individual atoms, then all phenomena are due to a continuum, and individual atoms do not exist. Because we have seen that we can predict fundamental constants with extreme precision using a combination of unitary evolution and measurement, then it must be that all physics processes obey unitary evolution. Because we have not isolated any process to date that is non-unitary, then all processes must be unitary. The conclusion that consciousness and free will eventually be explained by unitary evolution. The reasoning that if n particles are described by unitary evolution, then n plus 1 particles are described by unitary evolution. More generally, that there may exist thresholds for a given phenomena to occur. Note that thresholds exist throughout science. Consider nuclear processes. It may be that if n particles exist in a given state, that no nuclear reactions would take place, but if we include high energy particles that can cause fission, then such processes can occur. For a problem such as the measurement problem, we suggest that deductive reasoning is the appropriate scientific methodology. All ideas are on the table unless invalidated by theory or experiment. It is appropriate for problems that are not extensions of existing theory. Problems requiring deductive reasoning may have remained unsolved for long periods of time. Deductive reasoning may not produce results that are consistent with current theory. It requires truly thinking outside the box. How often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth? We know that he did not come through the door, the window, or the chimney. We also know that he could not have been concealed in the room, as there is no concealment possible. When, then, did he come? Says Sherlock Holmes in The Sign of the Four by Sir Arthur Conan Doyle. More information is useful in deductive reasoning, fully understanding the problem, characteristics of unitary evolution, history, are all critical tools for deductive reasoning. It is not as critical for inductive reasoning as one generalizes or extrapolates from current knowledge to arrive at a potential solution. For example, the history is not so important in order to propose an inductive solution to the problem. For problems with solutions that are strictly generalizations of existing theory, inductive reasoning is a good methodology to employ. One can derive results based on generalizing existing theory, which is good for engineering problems. Often, many ideas are simply rejected rather than being considered. Inductive reasoning is often faster for this reason than deductive reasoning, which requires eliminating all possibilities. You might be apprehensive if, when about to undergo surgery, the surgeon informs you that he plans to experiment and only use his deductive reasoning skills. Inductive reasoning often produces results that are consistent with current theory and expectations. Results can often be easily double-checked via different inductive arguments. It's interesting that Einstein appears to have moved from a deductive manner of thinking in his younger age to an inductive way of thinking in his older age regarding his criticism of quantum mechanics. In arguments with Bohr, Einstein's friend Paul Ehrenfest, a physicist from Leiden in Holland, said, "Einstein, I am ashamed of you. You are arguing against the new quantum theory just as your opponents argue about relativity theory." But even this friendly admonition went unheard. Wheeler, when speaking with Einstein in the 1940s, states, "This prescription reproduces all standard quantum theory. How could one ever want a simpler way to see what quantum theory is all about? Doesn't this marvelous discovery make you willing to accept quantum theory, Professor Einstein?" He replied in a serious voice, "I still cannot believe that God plays dice, but maybe," he said, "I have earned the right to make my mistakes." Perhaps, as one gets older, one tends to fall back on what one already knows, and thereby reason inductively. Well, if that's true, then we better get cracking, as we aren't getting any younger. A new theory will explain new things. But if there are still holes in our current understanding as to a theory that is yet undiscovered, red flags will generally occur. These red flags are clues for the deductive investigator. On the other hand, these clues are flatly rejected by the inductive investigator as errors that will be eventually explained with the current theory. Often, there is more than one red flag that is related to the same issue. Examples of red flags include the perihelion precession of Mercury found in 1859. It was known that it did not exactly follow Newton's equations. This was explained eventually by general relativity. The theory of ether was also found to be falsified by the Michelson-Morley experiment. Eventually it was explained by special relativity. And the extraordinary energy produced by the sun, which is produced by fusion, as we now know. It is often difficult to get new theory accepted, as the general population, most scientists, and many in academic circles actually favor inductive reasoning. One might think that philosopher-scientists would reason deductively. However, at the turn of the century, many were against Boltzmann's theory of atomism. These arguments were largely against abandoning the continuum for that which can't be seen, which is related to logical positivism. However, many came to accepting atomism later once experimental work confirmed the existence of atoms. Many people at this point perhaps have some sense of the differences between inductive and deductive reasoning, but still the concepts may not be as clear as they ought to be. We will introduce the use of the nexus of knowledge to further help illustrate several fine points of these concepts, and as well the limitations and shortcomings of inductive reasoning for certain classes of problems. The nexus of knowledge is a graph whereby any point represents a unique configuration for an experiment. In quantum terms, any point represents a unique quantum state of all the particles that compose an individual experimental arrangement. We'll denote the initial condition of the nexus as a blue circle. Each path emanating from an initial condition represents a potential time evolution of the experiment. Bifurcations are shown where there may be different outcomes for the same experiment. Bifurcations represent non-determinism. Each endpoint is an empirical outcome or result. The nexus of knowledge outcomes are empirically based. One can consider any endpoint as a new initial condition for a nexus. We will use blue paths to represent experimental phenomena or configurations of particles that have of yet no experimental or theoretical foundation to make predictions of the future outcomes. If it is found that when one starts in a given initial state, that one always evolves in the same manner to the same final state, then we say that the nexus of knowledge is fully deterministic for that initial state. One might also consider that it is possible to move in different ways, but that it always takes one to the same final state. In fact, when one considers Schrödinger's equation in terms of an action integral, a viewpoint such as this can be seen. And there are other possibilities, such as the possibility of a non-deterministic nexus with more than one possible final state. When theoretical predictions based on the current knowledge base and inductive reasoning have been verified to be correct within some error delta, the color of the associated path is updated to green. Now, as we learn more, and so our knowledge base continues to grow, we will find that the green paths continue to grow also. Now here's an example of a fully deterministic knowledge base within a non-deterministic nexus. Consider the case whereby experimental results lie outside the region described by the current knowledge base and inductive reasoning. Phenomena would exist that cannot be described by current theory or the use of induction based solely on current theory. These phenomena are necessarily exceptions to what is currently understood. A new theory that explains such phenomena might be initially met with skepticism and resistance, particularly by those who prefer inductive reasoning and are unskilled in deductive reasoning. Such was the case initially with Galileo's theory, Boltzmann's theory, and Einstein's theory of relativity. Scientists who use inductive reasoning might classify such phenomena as that which can be understood by current theory, but the detailed predictions are generally too complex. We will now consider categorizations and refinements of the nexus of knowledge. We will use black paths to represent phenomena for which no exact experiment has taken place to test a particular arrangement. However, there exists general theory and confirmed experimental evidence for similar arrangements. Yellow paths represent phenomena for which experiments or theory have called into question whether or not such phenomena can be accurately described by the current knowledge base. These paths may actually be green, and the experiments to date have been performed incorrectly, or they may be actually green, and the theoretical assumptions did not match the experiment. For example, if the theoretical modeling was too simplistic. Examples of yellow paths include the result of the Michelson-Morley experiment and the perihelion precession of Mercury. Gray paths are assigned to represent phenomena that have been verified at present to not be adequately described by current theory. Experiments are performed that prove within experimental error that a given theoretical prediction is wrong. An example of this is when Compton showed that every interaction, even at the single quantum level, conserved energy and momentum. This invalidated the BKS theory. A new theory was then needed to explain photon-matter interaction. Another historical example is the lamp shift experimental finding. Assign orange paths if no theory can ever exist to make predictions and one is forced to utilize empirical evidence. Now, many may argue the need to consider orange paths, but their arguments would be from an inductive standpoint. Orange paths are a logical possibility that have to be considered in a deductive reasoning investigation, whereby one is considering phenomenon that is not well described. Well, maybe you thought we were done with orange paths, but we assign red paths when? Can you use the deductive method to determine when we might assign red paths? Let us look at several examples to more fully understand inductive reasoning versus deductive reasoning. Example 1. An engineer learns how to correctly design and accurately predict the response of the design for various electrical engineering circuits. He learns to build and test circuits in school and verifies their behavior up to a level of accuracy as shown in green below. The engineer graduates from school, takes a job, and is asked to apply his knowledge learned and predict the behavior for a circuit that the engineer has never seen as shown in black, but the circuit is similar in nature to others that he has seen for which a theory exists to make predictions. The engineer then builds the circuit, tests it, and measures the outputs, and confirms that his predictions based on the current knowledge base are within an error delta. He is successful, and the color of the path associated with his circuit is changed to green. Example 2. The same engineer is given a new circuit to design as shown in black, one which he has not designed previously, but expects will work in conformity with the current knowledge base. The engineer applies the theory and practices he learned previously to design the desired circuit. He finds when he measures the outputs of the circuit that it does not agree with his expectations. The engineer is surprised by this finding and calls his teachers. They tell him that he must have done something wrong. These paths are yellow. Later it is found that the engineer's modeling of the experiment was not sufficiently accurate. For this problem, more accurate modeling was needed, and when this was done, the results agreed with the theory. We update these paths to green. The general form of the nexus is ultimately constrained by the principles of nature. It may be expected that a solution to the measurement problem will impose some structure to the physically realizable nexus. These examples indicate the following. An inductive reasoner sees the entire nexus of knowledge as green, even though it may not be. An inductive reasoner may be deceived unless the current state of knowledge is sufficiently advanced to where absolutely all phenomena can be predicted to within some delta. Inductive reasoning is to largely compute or apply knowledge that one has learned. There is generally a known methodology or approach that can be used to solve a problem inductively. Deductive reasoning may equally be applied to problems that will be predicted correctly using the current knowledge base. For example, mathematical theorems are generally based on deductive reasoning and are guaranteed to be self-contained within green paths. In such cases, deductive reasoning will yield the same result as inductive reasoning. When applying deductive reasoning to physical problems outside the knowledge base, the deductive solution may require rigor beyond any inductive argument. One needs to assure that the experimental conditions are correct to within the desired error delta needed to differentiate whether the problem is outside the current knowledge base or within the current knowledge base, but the modeling was not sufficient. a new theoretical basis is needed to explain the phenomena beyond anything known previously. And it is necessary to verify experimentally that the new proposed theory is correct and explain why the previous theory was inadequate. There is a time and place for the use of both deductive and inductive reasoning. Inductive reasoning is successful when a problem can be solved or accurately approximated based on building on existing theory and techniques. For this reason, many people in society may be completely successful only applying inductive reasoning throughout their lives. They may find deductive reasoning, when they come across it, to be rather foreign and question why someone would think in that manner. On the other hand, deductive reasoning must be considered when a problem cannot be solved via induction using the current knowledge base. One can make additional assumptions, but cannot be sure that the assumptions are correct. The statement, "How often have I said to you that when you've eliminated the impossible, whatever remains, however improbable, must be the truth," is rather applicable in the case of deductive reasoning for cases where the phenomena is outside the current knowledge base. The use of deductive reasoning for such cases will necessarily yield a different result than what is predicted by current theory, and thereby be initially considered improbable, surprising, and in certain cases even mystical.
Mysticism, ugh.
Schrödinger. Can we get the sound of mysticism from beyond the grave?
Okay, only this time.
Great, let's hear it. Well, that is a bit spooky. Thanks, Schrödinger. Let us continue. Deductive reasoning requires an approach to consider many potential solutions. Only the theory that cannot be eliminated is the correct answer. Any idea, no matter how far-fetched, must remain on the table until eliminated. In this case, the issues of consciousness and free will must be considered in any serious deductive attempt to solve the measurement problem. Engineers, architects, mechanics, etc. generally use inductive reasoning. Mathematicians often use deductive reasoning for proofs of theorems. Perhaps that is why mathematicians are often so weird. That was a joke. Thank you. Moving on. Fundamental scientists are often deductive thinkers. Bohr, Einstein, Maxwell. Can you think of another famous deductive thinker? Here is a hint. One can conclude from this presentation that we should look at the theory via inductive reasoning as accurately or very nearly true, until such time as other phenomena occur by which such theory will either 1. Be made more accurate, or 2. Liable to exception. Let us consider the methodology of breaking down a problem into a series of binary questions, in other words, those that have only 2 answers, such as yes, no. Then let us denote as m the minimum number of questions needed in order to solve a problem deductively. For simple problems, m may be 1 or 2. It is doubtful, however, that m is 1 or 2 for the measurement problem. We denote a deductive decision tree by a diagram where each fork with 2 paths represents each binary question, and where the depth of the tree is m. One sees that the number of possibilities that would need to be considered from the outset increases exponentially with m. A method of eliminating possibilities serially at the bottom row is rather inefficient. It would be typically more efficient to eliminate possibilities starting from the top and working downward. This only requires m steps in total and can reduce 2 to the m possibilities to a single correct solution. In this sense, first questions might be considered as the most important as they eliminate the most possibilities. So it is important to formulate the questions carefully in order to break the problem into a series of questions and to get the answers correctly, particularly the first few. The good news is that if one gets an incorrect answer, then eventually there should be contradictions as one works down an incorrect path. This will eventually lead one back to the correct path. The bad news is that this is inefficient, as in the worst case it would require to reach contradictions in all the incorrect paths in order to deduce where the incorrect path was taken. For example, if m equals 12 and one answers the first two questions incorrectly, then in the worst case, one may have to eliminate all remaining 2 to the m minus 2, or 1024, possibilities. In order to seriously examine the measurement problem, one should arm oneself with as many tools as possible. Full understanding of the problem, learn the history so that one can avoid the mistakes of the past and develop a good approach, and as well comprehend the general scientific approaches available and choose the approach that is most suitable. In this case, we suggest it is the deductive approach rather than the inductive approach that is the most suitable for the measurement problem. This video is a companion to our book, The Quantum Measurement Problem, published by Inspire Institute and available at Amazon.com. This book is the first volume of a book series entitled Progress on the Physics of Quantum Measurement. Be sure to visit our website, which has more videos and additional information on the quantum measurement problem at theqmp.com. We also have been working a long time on our own approach to resolving the measurement problem that involves closed systems that function as measurement devices. The details of the approach can be seen at internon.com.